Hey guys, tonight we explore the incredible journey of Egyptian engineers who transformed from simple mud brick makers into the master builders of the ancient world. You might imagine ancient engineering as primitive and crude, but the truth is Egyptian engineers developed techniques so advanced that modern architects still study their methods today. We're diving into 3,000 years of innovation that created some of humanity's most enduring monuments. Forget what Hollywood taught you about slaves building pyramids with whips and chains. The reality is far more fascinating and complex. These weren't just laborers moving stones. Egyptian engineers were mathematicians, astronomers, hydraulic specialists, and master craftsmen who solved problems that would challenge even today's construction teams. They developed precision tools, revolutionary lifting systems, and architectural principles that have survived millennia, from the first mastaba tombs to the Great Pyramid of Giza, from simple irrigation canals to massive temple complexes. Egyptian engineers continuously pushed the boundaries of what was possible. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here, and let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey. Together, welcome to ancient Egypt, where engineering wasn't just about building structures. It was about creating monuments that would speak to the gods themselves. Tonight, we'll follow the extraordinary 3,000-year evolution that transformed simple builders into the greatest engineers the ancient world had ever seen. You wake up in Egypt around 3,100 BCE, and you're about to witness the birth of engineering as we know it. The Nile has just receded from its annual flood, leaving behind rich, fertile mud that will become the foundation of civilization. But you're not just any observer. You're watching the first Egyptian engineers figure out how to transform this simple mud into something permanent, something that will last forever. The air is thick with the smell of wet earth and the sound of thousands of workers mixing mud with straw, their feet squelching in the mixture that will become the first building blocks of an empire. These early engineers aren't working with blueprints or CAD programs. They're inventing architecture as they go, solving problems that have never been solved before. You notice how they've already figured out that pure mud won't hold up to the elements. The straw reinforcement isn't just random bends. It's carefully measured, creating a composite material that's stronger than its individual components. Watch as they test different ratios, different types of straw, different drying techniques. This is engineering in its purest form, trial, error, and gradual perfection. The first mastaba tombs are rising from the desert floor, and you can see the engineers grappling with fundamental questions. How do you create a structure that will protect a pharaoh's body for eternity? How do you build something that won't collapse under its own weight? How do you orient a building to align with the stars? These questions drive innovation that will echo through millennia. These engineers are developing solutions that seem almost magical. They're creating ramps and levers to move blocks that weigh several tons. They're inventing the plumb line and the level, tools so fundamental that modern construction still depends on them. And this is just the beginning. They're laying the groundwork for engineering marvels that will astound the world for thousands of years. The morning sun casts long shadows across the construction sites, where teams of specialists are emerging: stonecutters, who understand rock like modern geologists, surveyors who can measure distances with remarkable accuracy, architects who visualize structures before they exist, and project managers who coordinate the work of hundreds. But engineering in ancient Egypt isn't just about individual brilliance. You're watching the birth of organized, systematic construction. These teams are developing a language of engineering, a way of communicating complex ideas about construction and design. The mud brick makers are becoming master craftsmen, understanding how temperature, humidity, and drying time affect their products. The stone workers are learning to read the grain of limestone and granite, finding the natural fracture lines that will make cutting more efficient. The surveyors are mapping the land with remarkable precision, creating the first engineering drawings in human history. They're developing mathematical relationships that govern proportion, stability, and beauty. You can see them working with ropes marked at regular intervals, creating perfect geometric shapes that will become the foundation for architectural harmony. And this is just the foundation. Over the next 3,000 years, these humble beginnings will evolve into engineering achievements that modern science still struggles to fully understand. The seeds of greatness are being planted in Nile mud and desert sand. You're standing in the engineering workshop of ancient Egypt around 2900 BCE, and the air is filled with the sound of measuring instruments being calibrated. The sweet scent of cedar wood mixes with the dust of crushed limestone as Egyptian engineers perfect the mathematical principles that will guide their construction for millennia. These aren't just builders anymore. They're becoming mathematicians, geometricians, and precision specialists who understand that eternal monuments require perfect measurements. The cubit rod in your hands feels surprisingly sophisticated. This isn't just a simple measuring stick. It's a precision instrument calibrated to the royal cubit, standardized across the entire kingdom. Egyptian engineers have realized that consistency is the key to large-scale construction. Every cubit rod is exactly 20.62 inches long, divided into 7 palms, each palm divided into 4 fingers. This standardization allows thousands of workers to collaborate on massive projects with unprecedented accuracy. You can see master craftsmen checking and rechecking these instruments, understanding that a small error in measurement could become a catastrophic failure in construction. Watch as the engineers work with their ropes and stakes, creating perfect right angles using the 3-4-5 triangle principle. They've discovered that a rope with 12 equal segments formed into a triangle with sides of 3, 4, and 5 segments will always create a perfect 90-degree angle. This mathematical principle, later known as the Pythagorean theorem, is being applied practically centuries before Pythagoras was born. The engineers move with confidence across the construction sites, creating perfect geometric shapes that will become the foundation for structures that will stand for millennia. The engineering teams are developing increasingly sophisticated tools. The Merket, a sighting instrument made from a straight bar with a plumb line, allows them to determine true north with remarkable accuracy. The Bay, a forked stick that works like a giant compass, helps them measure angles and distances across vast construction sites. These instruments might look simple, but they're enabling precision that rivals modern surveying equipment. The engineers understand that building for eternity requires accuracy that exceeds human perception. You notice how the engineers are obsessed with astronomical alignment. They're not just building tombs and temples, they're creating structures that will maintain perfect alignment with celestial bodies for thousands of years. The engineering calculations required for this are staggering. They must account for the precession of the equinoxes, the shifting of star positions over centuries, and the complex mathematics of celestial mechanics. Watch as teams of astronomer engineers work through the night, tracking star movements and calculating alignments that must remain true long after they're dead. The scribes are developing a sophisticated system of engineering notation. Hieroglyphic symbols represent not just words, but mathematical concepts, engineering specifications, and construction techniques. They're creating the world's first technical manuals, documents that will guide construction projects for generations. These aren't simple instruction sheets. They're comprehensive engineering specifications that include material requirements, construction sequences, quality standards, and safety procedures. Egyptian engineers are also mastering the mathematics of materials. They've calculated the load-bearing capacity of different stones, the optimal angles for ramps and inclines, and the precise ratios needed for mortar that will remain strong for millennia. Their mathematical models account for thermal expansion, settling, and the gradual effects of weathering. This mathematical precision extends to every aspect of construction. The engineers have calculated the exact number of workers needed for different tasks, the optimal work schedules to maximize productivity, and the precise quantities of materials required for projects that will span decades. And this is just the beginning. These mathematical foundations will enable Egyptian engineers to tackle increasingly ambitious projects, pushing the boundaries of what's possible with ancient technology. You're transported to the Giza Plateau around 2580 BCE, standing before the most ambitious engineering project in human history. The Great Pyramid of Khufu is rising from the desert, and you're witnessing engineering problem-solving on a scale that won't be matched for thousands of years. The morning sun casts long shadows across the construction site, where 20,000 workers are participating in humanity's greatest engineering challenge. The scale is almost incomprehensible. This single project will consume more stone than all the cathedrals of medieval Europe combined. The logistics alone are staggering. Egyptian engineers are coordinating the quarrying, transportation, and placement of 2.3 million stone blocks, each weighing between 2.5 and 15 tons. The limestone is being quarried from sites along the Nile, while the granite for the inner chambers is being transported from Aswan, over 500 miles away. The engineering precision required to coordinate this massive supply chain is mind-boggling. You can see supply masters tracking materials, calculating delivery schedules, and coordinating transportation that involves thousands of boats, sledges, and workers. Watch as the engineers solve the fundamental problem of lifting massive stones to heights of over 480 feet. They've developed a system of ramps that spirals around the pyramid as it rises, allowing workers to drag blocks to any height. But this isn't just brute force, it's sophisticated mechanical engineering. The ramps are built at precisely calculated angles, steep enough to conserve space, but gentle enough for teams of workers to manage the massive stones. The engineering calculations account for friction coefficients, load distributions, and the mechanical advantage of different pulling angles. The engineers have invented a variety of lifting devices that multiply human capability. Wooden levers, some over 20 feet long, multiply human strength by factors of 10 or more, allowing small teams to move blocks that would otherwise require hundreds of workers. Wooden rollers reduce friction, enabling massive stones to be moved across great distances with manageable effort. Rope and pulley systems, though simple by modern standards, represent revolutionary thinking about mechanical advantage. These aren't crude devices, they're precision-engineered machines designed for specific tasks. You notice the incredible precision of the pyramid's construction. The base covers 13.1 acres and is level to within just 2.1 centimeters. The sides are aligned to the cardinal directions with an accuracy of 3/60ths of a degree. This precision requires not just mathematical knowledge, but incredibly sophisticated surveying techniques and quality control systems. Teams of surveyors work constantly, checking alignments, measuring distances, and ensuring that the massive structure remains geometrically perfect as it rises. The engineering of the internal chambers is even more remarkable. The Grand Gallery, with its corbelled ceiling that rises 28 feet, demonstrates advanced understanding of structural engineering. The King's Chamber, built from enormous granite blocks, showcases precision cutting and fitting that modern machinery would struggle to match. The engineers have created a ventilation system that maintains air circulation throughout the pyramid's interior, using principles of fluid dynamics that won't be formally understood for thousands of years. Egyptian engineers are also solving complex problems of structural integrity. They've calculated how to distribute the pyramid's enormous weight, miners approximately 6.5 million tons, without causing catastrophic failure. Internal chambers are positioned to minimize stress concentration, and the pyramid's shape itself is optimized for stability. The engineers understand how stone behaves under compression, how weight distribution affects structural stability, and how to design internal spaces that don't compromise overall strength. The construction timeline reveals remarkable project management skills. The pyramid is being built in stages, with each phase carefully planned to maintain structural integrity while allowing continued construction. The engineers have developed sophisticated scheduling systems, coordinating the work of stonemasons, transporters, and specialized craftsmen. Materials flow like a precisely choreographed ballet, with thousands of workers performing specific tasks in perfect coordination. The pyramid's construction is also pushing the boundaries of materials science. The engineers have developed mortars that will remain flexible for millennia, preventing cracking as the structure settles. They've selected stones based on their geological properties, understanding how different types of limestone will behave over time. Quality control systems ensure that only the best materials are incorporated into the structure, and this is just one pyramid. Egyptian engineers are simultaneously managing multiple construction projects, each presenting unique challenges and requiring innovative solutions. You find yourself in the Fayum region around 2000 BCE, where Egyptian engineers are performing what can only be described as hydraulic magic. The air is filled with the sound of rushing water and the shouts of workers as they redirect the mighty Nile itself. These engineers aren't just building monuments anymore, they're reshaping the landscape, controlling the river that gives Egypt life. The engineering challenge is enormous. They must harness the annual flood while protecting civilization from its destructive power. The Nile floods annually, depositing fertile silt across the land, but also destroying crops and settlements if not properly managed. Egyptian engineers must harness this flood, directing the water where it's needed while protecting populated areas from destruction. They're creating one of the world's first large-scale hydraulic systems, engineering solutions that will serve as models for hydraulic engineering for thousands of years. You can see teams of engineers working with remarkable coordination. Their understanding of water flow and pressure allowing them to control forces that could destroy entire cities. Watch as the engineers construct massive earthwork dams and levees. These aren't simple piles of dirt. They're carefully engineered structures built from layers of clay, sand, and stone. The engineers have calculated the water pressure these structures must withstand, the seepage rates through different materials, and the effects of seasonal flooding on structural integrity. The construction techniques involve precise compaction, drainage systems, and erosion protection that demonstrate sophisticated understanding of soil mechanics and hydraulic forces. The canal systems are marvels of precision engineering. Channels must be cut at exactly the right grade to ensure water flows at the optimal rate. Too steep, and the water will erode the channels. Too shallow, and the water will stagnate. Egyptian engineers have developed sophisticated techniques for measuring and maintaining these precise gradients across distances of hundreds of miles. They use water levels, plumb lines, and geometric principles to achieve slopes measured in inches per mile, maintaining these gradients across terrain that varies dramatically in elevation and soil type. You notice the ingenious gate systems that control water flow. Wooden sluice gates, operated by complex lever mechanisms, allow engineers to direct floodwaters with remarkable precision. They can flood specific agricultural areas while keeping others dry, maximizing crop yields and minimizing damage. These gates are engineering marvels, designed to withstand enormous water pressure while remaining easily operable by small teams of workers. The mechanical systems use counterweights, gear trains, and leverage to multiply human effort, allowing precise control of massive water flows. The shaduf, a counterbalanced irrigation device, represents brilliant mechanical engineering. A long pole balanced on a fulcrum, with a weight on one end and a water bucket on the other, allows a single worker to lift water to heights that would otherwise require multiple people. This simple but effective machine multiplies human effort by factors of 5 or more, making irrigation possible in areas far from the river. The engineering principles involved leverage, counterbalancing, and mechanical advantage will become fundamental to all subsequent machine design. Egyptian engineers are also constructing massive reservoirs and cisterns. These structures must be waterproof, structurally sound, and capable of storing millions of gallons of water. The engineers have developed sophisticated concrete-like materials made from lime, sand, and crushed pottery that create watertight seals lasting for centuries. The structural design accounts for water pressure, soil loading, and thermal expansion, creating storage systems that remain functional for millennia. The engineering of the harbor systems is equally impressive. Artificial harbors are being carved from solid rock, with precise calculations ensuring that ships can navigate safely in all seasons. Breakwaters protect harbors from storms, while channel systems prevent silting that would make navigation impossible. The engineers understand tidal forces, current patterns, and sediment transport, designing harbor systems that work with natural forces rather than fighting them. Drainage systems in the cities represent advanced urban engineering. Underground sewers, lined with stone and designed with precise gradients, carry wastewater away from populated areas. These systems include access points for maintenance, overflow channels for flood conditions, and settling basins that prevent clogging. The engineering principles involved gravity flow, hydraulic capacity, and system redundancy create urban infrastructure that won't be matched in Europe,
for over 1,000 years. The engineers are also developing sophisticated water purification systems, sand filters, settling ponds, and ceramic filtration systems ensure that drinking water remains clean and safe. They understand the relationship between water quality and public health, implementing engineering solutions that prevent disease transmission and maintain population health. And this hydraulic mastery extends far beyond practical necessity. The engineers are creating ornamental fountains, reflecting pools, and water features that demonstrate their complete control over this essential element.
You're standing in the quarries of Aswan around 1500 BCE, watching Egyptian engineers tackle their most ambitious challenge, yet building temples that will serve as earthly homes for the gods. The granite beneath your feet is some of the hardest stone on earth, yet these engineers are cutting it with precision that would impress modern stonemasons. The temple complex at Karnak is rising in the distance, a testament to engineering skills that have been refined over 2 millennia. The scale of these projects dwarfs even the pyramids. Some temple complexes cover hundreds of acres and require decades to complete. The engineering challenges of temple construction are unlike anything tackled before. These structures must be massive enough to inspire awe, precise enough to maintain astronomical alignments, and durable enough to last for eternity. The engineers are working with stones that weigh up to 200 tons, moving them hundreds of miles and placing them with millimeter precision. The tolerances required exceed anything in previous construction. These buildings must function as both architecture and precision instruments. Watch as the engineers quarry the massive obelisks that will grace the temple entrances. These single pieces of granite, some over 100 feet tall and weighing 300 tons, must be cut from solid rock without creating a single crack. The engineers have developed techniques using wooden wedges, water and controlled heating to split granite along predetermined lines. The precision required is extraordinary. A single mistake could ruin months of work and waste materials that take years to quarry. The transportation of these massive stones requires engineering innovation on a grand scale. The engineers have constructed special barges capable of carrying 200-ton loads down the Nile. These aren't simple boats, they're floating construction platforms with sophisticated ballast systems and reinforced hulls designed specifically for heavy cargo transport. The loading and unloading of these massive stones requires elaborate crane systems and precisely calculated ramps that can handle loads that would crush normal infrastructure. You notice how the temple engineers have mastered the art of precision fitting. Massive stone blocks are cut and shaped so precisely that they fit together without mortar, creating joints so tight that a knife blade cannot be inserted between them. This requires not just skilled craftsmanship, but sophisticated measuring and marking systems that ensure each block is cut to exactly the right dimensions. Quality control systems check every block, rejecting any that don't meet the exacting standards required for temple construction. The engineering of the temple's internal spaces is equally impressive. Hypostyle halls with hundreds of massive columns require precise calculations of load distribution and structural stability. The engineers have developed sophisticated understanding of how to transfer the weight of massive stone roofs through columns to foundations, creating internal spaces that span enormous distances without support. The column designs themselves are engineering marvels, optimized to carry maximum loads while creating the visual impact required for religious ceremonies. The temple's astronomical alignments represent the pinnacle of engineering precision. The main axis of the temple must align with specific stars or solar phenomena, requiring not just mathematical calculation, but also understanding of how the Earth's movement affects these alignments over time. The engineers must account for the precession of the equinoxes, calculating how star positions will change over thousands of years. These calculations involve mathematics that won't be formally developed in Europe for centuries. Egyptian engineers are also pioneering new construction techniques. They've developed sophisticated lifting systems using ramps, levers, and counterweights to position massive stones at great heights. The ramps themselves are engineering marvels, built with precise gradients and reinforced to support enormous loads. Some ramps are temporary structures, larger than many buildings, requiring their own foundation systems and structural engineering. The temple's foundation systems represent advanced geotechnical engineering. The engineers must build on desert sand and limestone bedrock, creating foundations that will support millions of tons of stone without settling or shifting. They've developed sophisticated techniques for soil preparation, foundation design, and load distribution that ensure structural stability for millennia. The foundation work often requires excavating to bedrock and creating elaborate drainage systems to prevent water damage. The engineering of the temple's water systems is equally sophisticated. Sacred pools must be fed by underground springs or channels, requiring precise hydraulic calculations and sophisticated construction techniques. Drainage systems must handle both normal water flow and seasonal flooding while maintaining the temple's structural integrity. The water systems often include elaborate filtration and purification systems that ensure sacred water remains clean and pure. And these temples aren't just single structures, they're vast complexes with multiple buildings, courtyards, and auxiliary facilities, all requiring coordinated engineering planning and execution that spans decades. You're witnessing one of the most impressive feats of ancient engineering as you stand in the sandstone quarries of Gebel El Silsila around 1400 BCE. The air is filled with the rhythmic sound of copper chisels striking stone and the creak of wooden levers as Egyptian engineers extract massive blocks from the living rock. These aren't just quarry workers, they're geological engineers who understand stone like modern geologists, reading the subtle signs that indicate where the best building material can be found. The engineering begins with geological survey and site selection. Egyptian engineers have developed sophisticated understanding of stone quality, rock structure, and geological formation. They can identify the layers of sandstone, limestone, and granite that will provide the best building materials, understanding how geological forces have affected stone quality over millions of years. They can read the natural fracture patterns in rock, understanding how to work with the stone's natural grain to maximize both quality and efficiency. Watch as the engineers demonstrate their mastery of controlled stone cutting. They've developed techniques for splitting massive blocks from solid rock using wooden wedges, water, and fire. Holes are drilled in precise patterns along the intended fracture line. Wooden wedges are inserted, and water is poured over them. As the wood swells, it creates enormous pressure that splits the rock along the predetermined line. The precision of these operations is remarkable, The engineers can predict exactly how a block will split, accounting for internal stresses, grain patterns, and geological structure. The engineers have developed specialized tools for different types of stone. Copper chisels work well for limestone. Harder bronze tools are needed for granite, and wooden mallets prevent damage to cutting edges while providing the force needed for effective cutting. The tools themselves are engineering marvels, designed with specific angles and edge geometries that optimize cutting efficiency while minimizing tool wear. Tool maintenance and sharpening systems ensure that cutting implements remain effective throughout long quarrying operations. You notice the sophisticated transportation systems the engineers have developed. Massive stone blocks are moved from quarries to construction sites using elaborate ramps, rollers, and sledges. The ramps are engineering marvels in themselves, built with precise gradients and reinforced to support loads that would crush most modern roads. These temporary structures often require months to build and their own sophisticated engineering to ensure they can handle the massive loads they're designed to carry. The engineers have invented specialized transportation equipment for different types of loads. Heavy sledges with wooden runners distribute the weight of massive stones across large areas, preventing the sledges from sinking into sand or breaking through road surfaces. Teams of workers use sophisticated rope and lever systems to maintain control during transport, preventing accidents that could kill workers or damage irreplaceable stone blocks. River transportation requires even more sophisticated engineering. The engineers have designed special barges with reinforced hulls capable of carrying stones weighing hundreds of tons. These vessels must be carefully ballasted to maintain stability while loaded with such massive cargoes that would normally sink any boat. The loading and unloading systems use elaborate combinations of ramps, cranes, and counterweights that allow massive stones to be transferred between land and water transport without damage. Egyptian engineers have also mastered the art of precision measurement during quarrying operations. They've developed standardized cutting techniques that ensure blocks are cut to exact specifications, minimizing waste and ensuring perfect fit during construction. Quality control systems check every block for dimensional accuracy, structural integrity, and surface quality, ensuring that only the best stones are selected for important projects. The engineering of the quarry sites themselves is impressive. Access roads must be built to handle massive loads. Drainage systems must prevent flooding during the annual inundation, and work areas must be organized for maximum efficiency. The engineers have created industrial complexes in the desert, complete with housing for workers, workshops for tool maintenance, storage areas for completed blocks, and administrative facilities for managing complex operations. The workforce management represents another aspect of engineering excellence. Thousands of workers must be coordinated, fed, housed, and managed in remote locations. The engineers have developed sophisticated logistics systems that support large workforces in challenging environments, ensuring that quarrying operations can continue year-round despite extreme conditions. And the engineers are constantly innovating, developing new techniques for handling increasingly massive stones and tackling more challenging quarrying conditions that push the boundaries of what's possible with ancient technology. You're inside the pyramid of Amenemhat III around 1850 BCE, running your hands along stone joints so precise that they seem to be carved from single pieces of rock. The flickering light from oil lamps reveals masonry work that represents the pinnacle of Egyptian engineering achievement. These aren't just skilled craftsmen, they're precision engineers who have elevated stonework to an art form that modern masons struggle to match. The tolerances achieved here are measured in fractions of millimeters, created using only hand tools and incredible skill. The engineering precision required for this level of stonework is staggering. Each block must be cut to tolerances measured in fractions of millimeters, shaped to fit perfectly with its neighbors, and positioned with astronomical precision. The engineers have developed techniques and tools that allow them to achieve this level of accuracy using only hand tools and human skill, creating joints so tight that they remain perfect after thousands of years. Watch as the master masons demonstrate their cutting techniques. They've developed specialized tools for different aspects of stonework: the straight chisels for rough cutting, angled chisels for detailed work, and abrading stones for achieving perfectly smooth surfaces. The sequence of operations is carefully planned, with each step building on the previous one to achieve the final precision. The craftsmen work with rhythmic precision, their movements refined through years of practice and training. The measuring and marking systems are equally sophisticated. The engineers use wooden templates and patterns to ensure consistency across hundreds of blocks. Plumb lines and levels ensure that vertical and horizontal surfaces are perfectly aligned. String lines stretched between reference points allow workers to maintain precise alignments across vast distances. The accuracy achieved rivals modern surveying equipment, created using principles of geometry and careful craftsmanship. You notice how the engineers have mastered the art of stone shaping. They understand the internal structure of different types of stone, working with the natural grain to achieve maximum strength and durability. They've developed techniques for creating complex curved surfaces, angled cuts, and intricate decorative elements, all with hand tools and incredible skill. The understanding of stone properties allows them to optimize cutting techniques for different materials. The engineering of the mortar systems is equally impressive. Egyptian engineers have developed mortars that remain flexible for millennia, preventing cracking as structures settle and thermal expansion occurs. These mortars are carefully formulated from lime, sand, and organic additives, creating bonds that are often stronger than the stones themselves. The mortar chemistry is optimized for different applications and environmental conditions. The lifting and positioning systems represent mechanical engineering at its finest. The engineers have developed sophisticated techniques for moving massive stones into precise positions using combinations of ramps, levers, and human power. They can position blocks weighing several tons with millimeter precision, achieving fits so tight that no mortar is needed. The mechanical systems multiply human effort while maintaining precise control. Quality control systems ensure that only the best work is accepted. Master masons inspect each block, checking dimensions, surface finish, and structural integrity. Blocks that don't meet standards are rejected or reworked, ensuring that only perfect stonework is incorporated into the structure. The quality standards are maintained through rigorous inspection and apprenticeship systems that pass knowledge from generation to generation. The engineering of complex stone assemblies is particularly impressive. Multi-block arches, corbelled ceilings, and interlocking stone systems require sophisticated understanding of structural mechanics and precise execution. The engineers must calculate load distributions, stress concentrations, and potential failure modes for these complex systems,
ensuring that they remain stable under all conditions. Egyptian engineers have also developed specialized techniques for working with different types of stone. Limestone requires different cutting techniques than granite. Sandstone behaves differently than basalt, and each material has its own optimal methods for quarrying, shaping, and installation. The mastery of different materials allows engineers to select the best stone for each application. The surface finishing techniques represent another aspect of engineering excellence. The engineers have developed polishing and smoothing techniques that create surfaces of mirror-like quality. They understand how different abrasives affect different stones, achieving finishes that enhance both appearance and durability. Some surfaces are polished to optical quality, creating mirror-like finishes that remain perfect after millennia. And this precision extends to every aspect of construction, from the massive foundation blocks to the smallest decorative elements, demonstrating engineering excellence that permeates every detail of Egyptian construction.
You're crawling through the narrow passages of KV-55 in the Valley of the Kings around 1350 BCE, where Egyptian engineers are creating some of the most sophisticated underground structures in the ancient world. The air is stale and filled with stone dust as workers carve chambers deep into the limestone bedrock. These aren't just tomb builders, they're underground engineers tackling challenges that modern tunneling experts would find daunting. The engineering problems of underground construction require different solutions than surface building, demanding specialized techniques and tools. The engineering begins with geological survey and site selection. Egyptian engineers have developed sophisticated understanding of rock stability, groundwater flow, and structural integrity in underground conditions. They can identify the best locations for underground construction, avoiding areas prone to collapse or flooding while maximizing the stability of the excavated spaces. The geological knowledge required rivals modern understanding, achieved through centuries of experience and careful observation. Watch as the engineers demonstrate their excavation techniques. They've developed specialized methods for cutting through different types of rock, using controlled heating and cooling to create fractures along predetermined lines. The precision required is extraordinary. Tunnels must follow exact paths. Chambers must be excavated to precise dimensions, and the structural integrity of the surrounding rock must be maintained throughout the process. Any mistake could cause catastrophic collapse. The ventilation systems represent remarkable engineering innovation. Long underground passages require sophisticated air circulation to support workers and prevent the accumulation of dangerous gases. The engineers have developed natural ventilation systems using carefully positioned shafts and passages that create airflow through temperature and pressure differentials. These systems work without mechanical fans, using principles of fluid dynamics to maintain breathable air throughout complex underground networks. You notice the incredible precision of the underground chambers. Walls are cut perfectly vertical, floors are level to within millimeters, and ceiling heights are maintained with remarkable consistency. This requires not just skilled craftsmanship, but sophisticated surveying techniques adapted for underground conditions where normal measuring methods don't work. The engineers have developed underground surveying techniques that maintain accuracy despite the challenges of working in confined, dark spaces. The engineering of the tomb's internal systems is equally impressive. Drainage systems prevent water accumulation, while carefully designed passages direct any water flow away from critical areas. The engineers must account for seasonal water table changes, occasional flooding, and the long-term effects of water infiltration. The drainage systems often include complex networks of channels, sumps, and overflow systems that protect the tomb contents for millennia. Egyptian engineers have also mastered the art of underground structural support. They understand how to excavate large chambers without compromising the stability of the surrounding rock. Pillar systems, arch supports, and reinforced walls ensure that underground spaces remain stable for millennia. The structural calculations account for rock loading, stress concentrations, and long-term stability under changing conditions. The engineering of the tomb's security systems is particularly sophisticated. Hidden passages, false chambers, and elaborate ceiling systems are designed to protect the tomb's contents from robbers. These systems require precise engineering to function properly while maintaining the structural integrity of the tomb. Secret doors, hidden passages, and false walls demonstrate engineering ingenuity applied to security problems. The transportation of materials in underground spaces requires specialized engineering solutions. Ramps, lifting systems, and narrow passages must be designed to allow workers to move massive stone sarcophagi and other burial goods into the deepest chambers. The logistics of underground construction are incredibly complex, requiring specialized equipment and techniques developed specifically for confined spaces. Egyptian engineers have developed specialized lighting systems for underground work. Reflecting mirrors and carefully positioned oil lamps provide illumination while minimizing smoke and heat buildup. The engineers understand how to maintain working conditions in spaces where natural light never penetrates, using optical principles to distribute artificial light effectively. The engineering of the tomb's internal environment is equally important. Temperature and humidity control systems ensure that burial goods remain preserved for eternity. The engineers have developed techniques for creating stable microclimates in underground spaces, protecting organic materials from decay through environmental control that rivals modern museum conditions. And these underground engineering skills extend beyond tombs to include underground storage facilities, workshops, and even underground temples that demonstrate the versatility of Egyptian underground construction techniques. You're standing in the embalming workshop of the Temple of Put around 1200 BCE, where Egyptian engineers are applying scientific principles to ensure that both human bodies and architectural structures will survive for eternity. The air is heavy with the scent of natron, resins, and preservatives as these master engineers work to defeat time itself. This isn't just religion, it's sophisticated materials, science and engineering applied to the ultimate challenge of preventing decay and ensuring eternal preservation. The engineering of mummification represents advanced understanding of chemistry, biology, and materials science. Egyptian engineers have developed precise formulations of preservative chemicals, understanding how different substances interact with organic materials to prevent decay. They've created standardized procedures that ensure consistent results across thousands of mummifications, developing quality control systems that maintain effectiveness across centuries of practice. Watch as the engineers demonstrate their mastery of environmental control. The mummification process requires precise temperature and humidity conditions, maintained through sophisticated ventilation systems and climate control techniques. They've engineered workshops that provide optimal conditions for preservation work, using natural airflow and carefully positioned openings to maintain stable environments that optimize preservation effectiveness. The engineering of the preservation chemicals is equally impressive. The engineers have developed complex formulations of resins, oils, and salts that penetrate organic materials and prevent bacterial growth. These aren't simple mixtures, they're carefully balanced chemical systems designed to work together to achieve maximum preservation effectiveness. The chemistry involved demonstrates understanding of molecular interactions that won't be formally described for thousands of years. You notice how the engineers have applied these same principles to architectural preservation. They've developed stone treatments that protect carved surfaces from weathering, sealants that prevent water infiltration, and protective coatings that maintain the appearance and integrity of painted surfaces. The engineering understanding developed for mummification is being applied to monument preservation, creating integrated preservation systems that protect both organic and inorganic materials. The engineering of the burial chamber environments represents sophisticated understanding of atmospheric science. Sealed chambers must maintain stable conditions for millennia, preventing the temperature and humidity fluctuations that would damage both bodies and burial goods. The engineers have developed sealing systems that create hermetic environments while allowing for slight pressure equalization that prevents structural damage from atmospheric changes. Egyptian engineers have also mastered the engineering of preservation containers. Canopic jars, sarcophagi, and nested coffins are designed as integrated systems that protect their contents from environmental damage. These containers use sophisticated sealing techniques, protective materials, and structural design to ensure long-term preservation. The engineering involves understanding of material compatibility, atmospheric control, and long-term stability under varying conditions. The engineering of the preservation process itself is remarkable. Every step is carefully planned and executed according to precise procedures developed over centuries of experience. The engineers understand how different materials respond to preservation treatments, adjusting their techniques based on the specific requirements of each case. The process control systems ensure optimal results through careful monitoring and quality control. The quality control systems ensure consistent results across all preservation work. Master embalmers inspect each step of the process, checking chemical concentrations, treatment times, and environmental conditions. The engineers have developed standardized procedures that minimize variation and ensure optimal preservation results, creating documentation systems that maintain consistency across generations of practitioners. Egyptian engineers have also developed sophisticated understanding of materials, degradation, and aging processes. They can predict how different materials will behave over time, designing preservation systems that account for long-term chemical changes, structural settling, and environmental variations. This understanding allows them to create preservation systems that remain effective for millennia. The engineering of the preservation facility infrastructure is equally important. Workshops require specialized ventilation systems, chemical storage facilities, and waste disposal systems that maintain safe working conditions while ensuring optimal preservation results. The engineers have created industrial complexes dedicated to preservation work, complete with all the supporting infrastructure required for large-scale operations. And this preservation engineering extends beyond mummification to include the preservation of papyrus documents, wooden artifacts, textile materials,
and even architectural elements, demonstrating the broad application of Egyptian preservation science.
You're witnessing the installation of a massive obelisk at the Temple of Luxor around 1250 BCE, where Egyptian engineers are demonstrating mechanical engineering skills that won't be surpassed for centuries. The ground trembles as hundreds of workers operate sophisticated lifting machines, their coordinated efforts guided by engineers who have mastered the principles of mechanical advantage. These aren't just skilled craftsmen, they're mechanical engineers who have invented machines that multiply human strength and precision by extraordinary factors. The engineering begins with understanding the fundamental principles of mechanical advantage. Egyptian engineers have developed sophisticated understanding of levers, pulleys, and inclined planes, creating machines that allow small forces to move enormous loads. They've calculated the mechanical advantage of different systems, optimizing their designs for maximum efficiency while ensuring safety and reliability under extreme loads. Watch as the engineers demonstrate their mastery of lever systems. Massive wooden levers, some over 30 feet long, are positioned at precisely calculated points to lift stones weighing many tons. The engineers understand how to position fulcrums, calculate force requirements, and coordinate multiple levers to achieve controlled lifting and positioning. The mathematical calculations involved account for load distribution, stress concentration, and the coordinated timing required for safe operation. The pulley systems represent remarkable mechanical innovation. Although simple by modern standards, these systems demonstrate sophisticated understanding of force multiplication and direction change. The engineers have developed techniques for rigging complex pulley systems that allow precise control of massive loads while multiplying human effort by factors of 10 or more. The rope work involved requires specialized knowledge of fiber strength, knot systems, and load distribution. You notice the incredible precision of the inclined plane systems. The engineers have calculated optimal angles for ramps that allow workers to move massive stones while minimizing effort and maximizing safety. These ramps are engineering marvels, built with reinforced surfaces and precise gradients that maximize efficiency while ensuring safety. The construction of the ramps themselves often requires more engineering effort than the structures they're designed to serve. The engineering of the lifting platforms is equally impressive. Wooden scaffolding systems support workers and equipment at great heights, requiring sophisticated understanding of structural mechanics and load distribution. These platforms must be strong enough to support enormous loads while remaining light enough to be easily assembled and repositioned. The structural calculations account for wind loading, dynamic forces, and safety factors that ensure worker protection. Egyptian engineers have also developed specialized mechanical devices for specific tasks. The Shaduf irrigation system uses counterbalanced levers to lift water with minimal human effort. Specialized cranes use combinations of levers and pulleys to position massive stones with millimeter precision. Each device is optimized for its specific application, demonstrating engineering specialization that maximizes effectiveness for particular tasks. The engineering of the rope and cable systems is particularly sophisticated. The engineers have developed techniques for manufacturing ropes with specific strength characteristics, understanding how different fibers and twisting patterns affect performance under load. They've created standardized rope systems that ensure consistent performance across different applications, with quality control systems that maintain reliability under extreme conditions. The coordination of mechanical systems requires sophisticated project management and communication systems. The engineers must coordinate the operation of multiple machines, ensuring that forces are applied at precisely the right moments and in the right directions. This requires not just mechanical understanding, but also remarkable organizational skills in communication systems that coordinate hundreds of workers. Egyptian engineers have also developed comprehensive maintenance and repair systems for their mechanical devices. They understand how wooden components wear and fail under stress, developing replacement schedules and repair techniques that ensure continuous operation throughout long construction projects. The maintenance systems include spare parts manufacturing, component testing, and replacement procedures that minimize downtime. The engineering of the mechanical systems also includes extensive safety considerations. The engineers have developed techniques for controlling massive loads, preventing accidents that could kill workers or damage irreplaceable structures. They understand the failure modes of their systems and have developed procedures for safe operation that account for human error and equipment failure. And these mechanical engineering skills are being applied to increasingly complex projects, pushing the boundaries of what's possible with ancient technology while maintaining the safety and precision required for monumental construction. You're standing on the elevated platform of a surveyor's tower in the planned city of Akhetaten around 1350 BCE, watching as Egyptian engineers create what may be the world's first comprehensively planned city. The morning sun illuminates a geometric masterpiece spreading across the desert, where every street, building, and district has been positioned according to sophisticated engineering principles. These aren't just city builders, they're urban engineers who understand how to create functional, beautiful, and efficient urban environments that serve complex social and economic needs. The engineering begins with comprehensive site analysis and master planning. Egyptian engineers have surveyed the entire area, understanding topography, drainage patterns, prevailing winds, soil conditions, and geological stability. They've created detailed maps and plans that guide every aspect of city construction, from the grandest temples to the smallest residential areas. The planning process accounts for population growth, economic development, and the complex infrastructure requirements of urban life. Watch as the engineers demonstrate their mastery of urban water systems. The city requires sophisticated infrastructure to provide clean water to thousands of residents while removing waste and stormwater safely and efficiently. They've designed integrated systems of wells, channels, and drainage that work together to maintain urban hygiene and health. The water systems include distribution networks, waste treatment facilities, and flood control systems that ensure reliable urban services. The engineering of the street systems is equally impressive. Roads are laid out in geometric patterns that facilitate traffic flow while providing efficient access to all areas of the city. The engineers have calculated optimal street widths, intersection designs, and traffic patterns that minimize congestion and maximize functionality. The street systems include provisions for different types of traffic, from pedestrians to heavy cargo vehicles carrying construction materials. You notice how the engineers have integrated industrial and residential areas with sophisticated zoning principles. Workshops, storage facilities, and manufacturing areas are positioned to minimize environmental impact on residential neighborhoods, while maintaining efficient transportation links. The engineers understand how to balance economic needs with quality of life considerations, creating urban environments that support both commerce and comfortable living. The engineering of the city's infrastructure systems is remarkable. Sophisticated drainage networks handle both normal wastewater and seasonal flooding, using gravity flow and carefully calculated hydraulic systems. Underground systems carry waste away from populated areas, while surface channels direct stormwater to collection areas outside the city. The infrastructure includes redundant systems that ensure continued operation even during emergencies. Egyptian engineers have also mastered the art of urban microclimate management. They understand how building orientation, street layout, and vegetation can create cooler, more comfortable urban environments. The city is designed to channel cooling breezes while providing shade and protection from the harsh desert sun. The microclimate engineering creates urban environments that are significantly more comfortable than the surrounding desert. The engineering of the city's supply and distribution systems is equally sophisticated. Storage facilities, distribution networks, and transportation systems ensure that food, materials, and goods can be efficiently distributed throughout the urban area. The engineers have calculated the logistics requirements for supporting large urban populations, creating supply systems that maintain reliability even during peak demand periods. The integration of religious and administrative functions requires sophisticated planning that balances practical requirements with symbolic and ceremonial needs. Temple complexes, government buildings, and public spaces are positioned to create functional relationships while maintaining proper religious and social hierarchies. The engineers must coordinate multiple complex requirements while maintaining overall urban functionality. Egyptian engineers have also developed sophisticated understanding of urban security and defensive planning. The city's layout includes defensive considerations, with walls, gates, and defensive positions integrated into the overall design. The engineers understand how to create secure urban environments while maintaining functionality and accessibility for normal commercial and social activities. The engineering of the city's communication and administrative systems ensures efficient coordination of urban activities. Signal towers, messenger routes, and administrative networks allow information to be quickly transmitted throughout the urban area. The engineers have created integrated communication systems that support the complex coordination required for effective urban management. And this urban engineering represents the culmination of centuries of engineering development, bringing together expertise in hydraulics, construction, materials, science, and logistics to create comprehensive urban environments that serve as models for city planning. You're standing on the banks of the Nile at Memphis around 1100 BCE, watching Egyptian engineers launch the largest vessel ever built in the ancient world. The massive cedar ship stretches over 200 feet in length, its hull reinforced with sophisticated engineering techniques that allow it to carry loads that would sink lesser vessels. The air is filled with the scent of pitch and cedar as these master shipbuilders demonstrate naval engineering skills that won't be matched for centuries. The engineering begins with advanced understanding of hydrodynamics and naval architecture. Egyptian engineers have developed sophisticated knowledge of hull design, understanding how different shapes affect stability, speed, and cargo capacity under various loading and weather conditions. They've created standardized designs optimized for different purposes: river transport, sea voyages, ceremonial vessels, and military ships, each requiring different engineering solutions. Watch as the engineers demonstrate their mastery of ship construction techniques. The hull is built using sophisticated joinery methods that create flexible, watertight structures capable of handling the stresses of heavy loads and rough water. Cedar planks are carefully selected and shaped, joined with mortise and tenon joints that distribute stress throughout the structure while maintaining flexibility that prevents cracking under load. The engineering of the waterproofing systems is equally impressive. The engineers have developed sophisticated caulking techniques using combinations of rope, pitch, and resin that create watertight seals between hull planks. These systems must remain flexible as the wood expands and contracts with moisture changes, while maintaining complete water exclusion under all conditions. The waterproofing chemistry demonstrates understanding of material properties that ensures long-term effectiveness. You notice the incredible sophistication of the rigging and sail systems. Egyptian engineers have developed efficient sail designs that maximize wind capture while maintaining vessel control under varying wind conditions. The rigging systems use sophisticated rope and pulley arrangements that allow small crews to control enormous sails, adjusting sail position and shape to optimize performance while maintaining safety under all conditions. The engineering of the steering systems represents remarkable innovation in mechanical control systems. Large vessels require powerful steering mechanisms that allow precise control despite enormous loads and strong currents. The engineers have developed steering oar systems with mechanical advantage that enable helmsmen to control vessels that would otherwise be unmanageable, using lever systems and multiple steering positions that provide reliable control. Egyptian engineers have also mastered the engineering of specialized vessel systems for different applications. Cargo ships require sophisticated loading and unloading equipment, crane systems, and cargo securing methods that maximize capacity while ensuring safety. Ceremonial vessels need ornate decorative elements that don't compromise structural integrity. Military vessels require armor and weapon mounting systems that maintain vessel stability and performance under combat conditions. The engineering of the harbor and docking facilities is equally sophisticated. Artificial harbors carved from solid rock must accommodate vessels of different sizes while protecting them from storms and currents. Quay systems, loading facilities, and dry dock areas require precise engineering to function effectively, including drainage systems, structural supports, and material handling equipment. The navigation systems represent advanced understanding of astronomy and geography applied to maritime operations. Egyptian engineers have developed sophisticated techniques for determining position and direction using celestial observations, creating navigation instruments and charts that allow vessels to navigate accurately across vast distances. The navigation systems include backup methods and cross-checking procedures that ensure reliability. The engineering of the vessel maintenance systems is remarkable. Large ships require continuous maintenance to remain seaworthy, and the engineers have developed comprehensive systems for hull repair, sail replacement, and equipment maintenance. They understand how different materials degrade in marine environments and have developed preservation techniques that extend vessel life while maintaining performance and safety. Egyptian engineers have also developed sophisticated understanding of cargo handling and ship stability. They can calculate load distributions that maximize cargo capacity
while maintaining vessel stability and safety under all sea conditions. Loading systems and cargo securing techniques ensure that vessels can carry maximum loads safely while maintaining proper trim and stability. And these naval engineering skills are being applied to increasingly ambitious projects, including expeditions to distant lands and the construction of massive ceremonial vessels that demonstrate Egyptian engineering mastery to the known world.
You're standing in the copper smelting complex at Timna around 1150 BCE, where Egyptian engineers are demonstrating metallurgical skills that represent the cutting edge of ancient technology. The furnaces roar with carefully controlled fires as molten metal flows like liquid fire, guided by engineers who understand the complex chemistry of metal production. The air shimmers with heat and fills with the acrid smell of sulfur as these master metallurgists transform raw ore into the tools and weapons that build and defend an empire. The engineering begins with sophisticated understanding of ore geology and mining techniques. Egyptian engineers have developed advanced methods for identifying and extracting metal ores from desert mines, understanding geological formation processes that concentrate metals in specific locations. They understand how to follow ore veins, shore up underground workings, and extract maximum metal content from available ores through systematic mining techniques. Watch as the engineers demonstrate their mastery of furnace design and operation. These aren't simple fires, they're sophisticated chemical reactors designed to achieve and maintain the precise temperatures required for metal smelting. The furnaces use carefully designed airflow systems, refractory materials, and fuel management techniques that maximize efficiency while ensuring consistent results and optimal metal quality. The engineering of the smelting process represents advanced understanding of chemistry and materials science. The engineers have developed precise formulations of flux materials that remove impurities from metal ores, understanding chemical reactions that separate valuable metals from waste rock. They understand how different additives affect the smelting process, adjusting their techniques based on ore composition and desired metal properties. You notice the incredible precision of the temperature control systems. Different metals require different smelting temperatures, and the engineers have developed techniques for achieving and maintaining precise thermal conditions throughout the smelting process. They use visual cues, timing methods, and empirical testing to ensure optimal smelting conditions while maximizing yield and metal quality. The engineering of the casting and forming systems is equally impressive. Molten metal must be precisely controlled and directed into molds that create tools, weapons, and decorative objects with exact specifications. The engineers have developed sophisticated casting techniques that produce consistent results with minimal waste and maximum quality, using mold designs that account for metal shrinkage and thermal effects. Egyptian engineers have also mastered the art of alloy creation and metallurgical chemistry. They understand how different metals can be combined to create materials with superior properties, developing bronze alloys that are far superior to pure copper implements. Bronze, created by combining copper and tin in precise ratios, represents sophisticated metallurgical engineering that produces tools and weapons with optimal hardness, strength, and durability. The engineering of the metalworking tools and techniques is remarkable, The engineers have developed specialized hammers, anvils, and forming tools that allow precise shaping of metal objects under controlled conditions. They understand how to work metals at different temperatures using controlled heating and cooling cycles to achieve desired mechanical properties through heat treatment processes. The quality control systems ensure consistent metal quality across all production. Master metallurgists test metal samples using standardized procedures, checking composition, hardness, and structural integrity through empirical testing methods. They've developed standardized procedures that ensure only the best metal products are accepted for important applications, maintaining quality standards that ensure reliability. The engineering of the workshop infrastructure is equally important for successful metallurgical operations. Metallurgical operations require specialized ventilation systems that remove toxic fumes, fuel storage facilities that ensure continuous operation, and waste disposal systems that handle slag and other byproducts safely. The engineers have created industrial complexes that support large-scale metal production while maintaining safe working conditions. Egyptian engineers have also developed sophisticated understanding of metal preservation and maintenance. They understand how different metals corrode and degrade under various environmental conditions, developing protective treatments and maintenance procedures that extend the life of metal objects. The preservation techniques include surface treatments, protective coatings, and storage methods that prevent degradation. And these metallurgical engineering skills are constantly evolving as engineers experiment with new techniques and materials to create ever better tools and weapons that provide Egyptian civilization with technological advantages over their neighbors. You're witnessing the construction of the Great Hypostyle Hall at Karnak around 1250 BCE, where Egyptian engineers are pushing architectural design beyond anything previously imagined. The forest of massive columns rising around you represents engineering innovation that creates internal spaces on a scale that won't be matched for over 1,000 years. The morning light, filtering through the clerestory windows, illuminates stone craftsmanship that transforms architecture into art while maintaining structural integrity that will last for millennia. The engineering challenge is enormous and unprecedented. The hall covers 54,000 square feet and contains 134 columns, some reaching heights of 69 feet and measuring 33 feet in circumference. The engineers must create a structural system that supports massive stone roofing while maintaining the open, awe-inspiring internal space required for religious ceremonies involving thousands of participants. Watch as the engineers demonstrate their mastery of column design and construction. These aren't simple cylindrical supports, they're sophisticated structural elements designed to carry enormous loads while creating maximum visual impact. The engineers have calculated the optimal column spacing, base dimensions, and capital designs that maximize both structural efficiency and aesthetic effect while ensuring long-term stability under all loading conditions. The engineering of the foundation systems represents advanced understanding of soil mechanics and load distribution under extreme conditions. The massive columns require foundations capable of supporting loads measured in thousands of tons without settlement or failure. The engineers have developed techniques for soil preparation, foundation design, and load transfer that ensure structural stability for millennia despite challenging soil conditions and seismic activity. You notice the incredible sophistication of the roofing systems and structural engineering. Massive stone slabs spanning between columns must be precisely cut and positioned to create weatherproof coverage while distributing loads safely to the supporting structure. The engineers have developed lifting and positioning techniques that allow precise placement of stones weighing many tons at heights of over 60 feet, using only human power and mechanical advantage. The engineering of the lighting systems is equally impressive and innovative. The clerestory windows in the central nave provide natural lighting while maintaining structural integrity and weather protection. The engineers have calculated window sizes and positions that maximize interior illumination while ensuring that the roof structure remains stable and that rainwater is effectively excluded from interior spaces. Egyptian engineers have also mastered the art of architectural acoustics and environmental control. The hall is designed to enhance the sound of religious ceremonies with column spacing and surface treatments that create optimal acoustic conditions for chanted prayers and ceremonial music. The engineers understand how architectural elements affect sound transmission and have designed spaces that enhance rather than interfere with ceremonial activities. The engineering of the decorative systems represents remarkable integration of art and structure. Carved reliefs, painted surfaces, and sculptural elements are integrated into the architectural design without compromising structural integrity or weather resistance. The engineers have developed techniques for creating elaborate decorative schemes that enhance rather than weaken the building structure while providing surfaces that remain beautiful for millennia. The construction logistics for such a massive project require sophisticated project management and coordination systems. The engineers must coordinate the work of thousands of craftsmen, manage the supply of materials from distant quarries, and maintain construction schedules that span decades while ensuring consistent quality and safety. The organizational systems required are as impressive as the engineering techniques. The engineering of the building's environmental systems is equally sophisticated and innovative. Ventilation systems maintain comfortable conditions within the massive hall using natural airflow and thermal effects, while drainage systems protect the structure from water damage during seasonal flooding. The engineers have created building systems that function effectively despite the scale and complexity of the architecture. Egyptian engineers have also developed innovative construction techniques specifically for this project. New lifting methods, improved stone cutting techniques, and advanced surveying systems allow them to achieve precision and quality that exceeds even their own previous standards, while working at unprecedented scales and heights. And this architectural innovation represents just one example of how Egyptian engineers are constantly pushing the boundaries of what's possible with ancient technology while maintaining the quality and precision that ensures these structures will inspire future generations. You're standing in the observatory at Dendera around 50 BCE, where Egyptian engineers have created the most sophisticated timekeeping systems in the ancient world. The ceiling above you depicts a star map of unprecedented accuracy, while around you stand instruments capable of measuring time with precision that rivals modern chronometers. These aren't just astronomers, they're precision engineers who have learned to capture and measure time itself with mathematical accuracy that won't be surpassed for centuries. The engineering begins with sophisticated understanding of astronomical cycles and celestial mechanics. Egyptian engineers have observed and recorded the movements of stars, planets, and the sun with remarkable precision over thousands of years, creating mathematical models that predict celestial events with extraordinary accuracy. They've developed the longest continuous astronomical record in human history, providing the database needed for precision timekeeping. Watch as the engineers demonstrate their mastery of sundial design and construction. These aren't simple shadow-casting devices. They're precision instruments calibrated to local latitude and designed to maintain accuracy throughout the year. Despite seasonal variations in solar elevation, the engineers have developed complex mathematical formulations that account for the changing angle of the sun and the equation of time that compensates for Earth's orbital variations. The engineering of the water clock systems represents remarkable innovation in precision mechanics and flow control. These devices use carefully controlled water flow to measure time intervals with impressive accuracy, maintaining consistent timekeeping regardless of weather conditions or seasonal variations. The engineers have developed sophisticated flow control systems, standardized vessel designs, and calibration techniques that ensure consistent timekeeping performance over long periods. You notice the incredible precision of the astronomical instruments and measurement systems. The Merkit and Bay systems allow accurate measurement of star positions and celestial angles with remarkable precision. These instruments are calibrated to tolerances measured in arc minutes, requiring sophisticated understanding of optical principles and mechanical precision that rivals modern surveying equipment. The engineering of the calendar systems represents advanced mathematical and astronomical knowledge applied to practical timekeeping needs. The Egyptian calendar, with its 365-day year and sophisticated leap year corrections, demonstrates understanding of astronomical cycles that won't be improved upon for centuries. The engineers have created calendar systems that maintain accuracy over thousands of years while serving religious, agricultural, and administrative needs. Egyptian engineers have also mastered the engineering of seasonal time measurement and agricultural coordination. They understand how daylight hours change throughout the year and have developed timekeeping systems that account for these variations while coordinating agricultural activities with seasonal changes. Their seasonal calendars coordinate planting, irrigation, and harvesting with remarkable precision that maximizes agricultural productivity. The engineering of the star maps and celestial charts is equally impressive and scientifically advanced. These aren't just artistic representations, they're precision engineering drawings that accurately depict star positions, constellation relationships, and celestial movements with mathematical accuracy. The engineers have developed projection techniques that represent the three-dimensional sky on two-dimensional surfaces while maintaining positional accuracy. The integration of timekeeping with architectural design represents sophisticated engineering coordination. Temples and monuments are oriented to mark specific astronomical events, requiring precise calculations that coordinate building alignment with celestial movements over thousands of years. The engineers have created architectural calendars that mark important dates through shadow patterns and light effects that remain accurate across centuries. The engineering of the timekeeping instruments requires sophisticated understanding of materials, science, and precision manufacturing. Water clocks require precisely calibrated openings
and flow control systems, sundials need accurately positioned gnomons and precisely graduated scales, and astronomical instruments demand exactly shaped and positioned components that maintain accuracy under all environmental conditions. Egyptian engineers have also developed comprehensive timekeeping systems that coordinate different types of time measurement. Solar time, sidereal time, and seasonal time are all integrated into comprehensive systems that serve religious, agricultural, and administrative needs, while maintaining consistency across the entire kingdom. And these timekeeping engineering skills represent the culmination of thousands of years of astronomical observation and mathematical development, creating time measurement systems that serve as the foundation for all subsequent chronological science.
You're standing in the experimental workshop of the House of Life at Memphis, around 300 BCE, where Egyptian engineers are creating materials that don't exist in nature. The air is filled with the acrid smoke of chemical experiments. As these master materials, scientists develop new substances with properties specifically designed for engineering applications. These aren't just craftsmen following traditional recipes. They're materials engineers who understand the molecular basis of material properties and can design substances with predetermined characteristics. The engineering begins with sophisticated understanding of natural materials and their properties at the fundamental level. Egyptian engineers have systematically studied the characteristics of different stones, metals, organic materials, and natural compounds through centuries of empirical research. They've developed comprehensive knowledge of how materials behave under different conditions and how their properties can be modified through chemical and physical treatments. Watch as the engineers demonstrate their mastery of concrete and mortar formulation. These aren't simple mixtures of available materials. They're precisely engineered composite materials designed for specific applications and environmental conditions. The engineers have developed formulations that remain strong and flexible for millennia, resist water penetration under extreme conditions, and maintain their properties under temperature variations and seismic loading. The engineering of glass and ceramic materials represents remarkable innovation in high-temperature chemistry and materials processing. The engineers have developed sophisticated furnace systems capable of achieving and maintaining the precise temperatures required for glass formation while controlling atmospheric conditions. They understand how different additives affect glass properties, creating materials with specific optical, mechanical, and chemical characteristics for specialized applications. You notice the incredible sophistication of the metallic alloy development and metallurgical chemistry. Egyptian engineers have moved far beyond simple bronze creation, developing complex alloys with precisely controlled properties for specific applications. They understand how different metals interact at the atomic level, how cooling rates affect crystal structure and mechanical properties, and how mechanical working affects material performance under stress. The engineering of organic material preservation represents advanced understanding of chemistry and biology applied to materials science. The engineers have developed sophisticated treatments that prevent decay, maintain flexibility, and preserve appearance in organic materials over extremely long periods. These preservation systems use complex chemical formulations that work at the molecular level to prevent degradation processes. Egyptian engineers have also mastered the art of composite material creation and advanced materials engineering. They understand how different materials can be combined to create substances with properties superior to their individual components, developing fiber-reinforced composites, layered materials, and hybrid substances that demonstrate sophisticated materials engineering principles applied to construction and manufacturing. The engineering of surface treatments and coatings is equally impressive and scientifically advanced. The engineers have developed protective and decorative coatings that enhance material properties while providing aesthetic appeal and environmental protection. These coatings use sophisticated chemistry to bond permanently with substrate materials while providing specific functional properties such as water resistance or decorative appearance. The quality control systems ensure consistent material properties across all production operations. Master materials engineers test samples using standardized procedures, checking mechanical properties, chemical resistance, and long-term stability through empirical testing methods that predict material performance. They've developed empirical testing methods that predict material performance under different conditions and loading scenarios. The engineering of the production processes is equally important for consistent material quality. Materials engineering requires precise control of temperature, timing, atmospheric conditions, and chemical concentrations throughout manufacturing processes. The engineers have developed sophisticated process control systems that ensure consistent results while maximizing yield and minimizing waste. Egyptian engineers have also developed comprehensive understanding of material failure modes and degradation mechanisms. They can predict how materials will behave over time under various environmental conditions, designing material systems that account for aging, environmental exposure, and mechanical stress while maintaining performance over extremely long periods. And these materials engineering capabilities are constantly expanding as engineers develop new formulations and techniques for creating ever better materials that provide enhanced performance for increasingly demanding applications. Where you're witnessing something unprecedented in the regulatory complex at Lake Moeris around 230 BCE, where Egyptian engineers have created what can only be described as hydraulic computers. Water flows through precisely engineered channels, gates, and measuring devices that perform calculations and control massive irrigation systems with mechanical precision that rivals modern automated systems. These aren't just water management systems, they're hydraulic computing machines that process information and make decisions using only water flow and mechanical components. The engineering begins with sophisticated understanding of fluid dynamics and flow control applied to information processing. Egyptian engineers have developed mathematical models of water behavior that allow them to predict and control flow rates, pressure distributions, and system responses with remarkable accuracy. They've created the theoretical foundation for hydraulic computing by understanding how water flow can represent and process information. Watch as the engineers demonstrate their mastery of hydraulic logic systems and automated control. Water gates that open and close based on flow conditions, measuring devices that trigger responses when water levels reach specific thresholds, and timing systems that coordinate complex operations across vast irrigation networks. These mechanical systems perform logical operations using only water pressure and mechanical advantage while maintaining accuracy and reliability. The engineering of the measurement and control systems is equally impressive and scientifically advanced. Precisely calibrated weirs, flow meters, and level sensors provide accurate information about water conditions throughout the system with precision that rivals modern instrumentation. This information is processed by mechanical systems that automatically adjust gate positions, redirect flows, and coordinate system responses without human intervention. You notice the incredible sophistication of the hydraulic memory systems and data storage, water storage devices that maintain pressure levels, accumulator systems that store hydraulic energy for peak demand periods, and buffer systems that smooth out flow variations while maintaining system stability. These systems allow hydraulic computers to maintain stable operation despite variable input conditions and changing demand patterns. The engineering of the hydraulic communication systems represents remarkable innovation in information transmission. Water pressure signals can be transmitted over long distances through carefully designed channel systems, allowing coordinated control of irrigation networks spanning hundreds of miles. The engineers have created hydraulic communication protocols that ensure reliable information transmission while maintaining signal integrity over long distances. Egyptian engineers have also mastered the art of hydraulic amplification and signal processing. Small control signals can be amplified through mechanical systems to operate massive gates and valves while maintaining precision control. The engineers understand how to design amplification systems that maintain precision while providing enormous mechanical advantage, creating systems that can control massive infrastructure with minimal input energy. The engineering of the system integration is equally impressive and demonstrates advanced systems thinking. Multiple hydraulic subsystems must work together seamlessly, sharing information and coordinating responses to changing conditions while maintaining overall system stability. The engineers have developed system architectures that ensure reliable operation of complex hydraulic networks under all operating conditions. The maintenance and calibration systems ensure consistent performance across the entire hydraulic network. The engineers have developed procedures for testing and adjusting hydraulic components, maintaining system accuracy despite wear and environmental changes. They understand how hydraulic systems degrade over time and have developed maintenance schedules that prevent system failures while maintaining precision. The engineering of the hydraulic programming systems allows operators to modify system behavior without rebuilding hardware components. Adjustable weirs, movable gates, and reconfigurable channels allow the same hydraulic computing system to perform different functions as requirements change, providing flexibility that adapts to changing agricultural and water management needs. Egyptian engineers have also developed sophisticated diagnostic systems for hydraulic networks that enable troubleshooting and optimization. They can identify problems in complex systems, trace malfunctions to specific components, and predict system failures before they occur, ensuring continuous operation of critical water management infrastructure. And these hydraulic computing capabilities represent the pinnacle of Egyptian engineering achievement, demonstrating mastery of fluid dynamics, mechanical engineering, and system integration that won't be matched for over 1,000 years. You're standing in the sanctuary of the Temple of Edfu around 100 BCE, where Egyptian engineers have created acoustic environments so sophisticated that every whispered prayer reaches the ears of the gods with perfect clarity. The stone walls around you have been shaped and positioned with mathematical precision to enhance focus and direct sound in ways that modern acoustic engineers struggle to achieve. These aren't just religious buildings, they're precision-engineered acoustic instruments built from stone that demonstrate mastery of sound science. The engineering begins with sophisticated understanding of sound propagation and acoustic principles applied to architectural design. Egyptian engineers have developed mathematical models of how sound waves behave in enclosed spaces, understanding reflection, absorption, resonance, and interference effects with precision that rivals modern acoustic science. They've applied this knowledge to create acoustic environments optimized for specific ceremonial and functional purposes. Watch as the engineers demonstrate their mastery of acoustic design through architectural elements and spatial geometry. Column spacing, wall curvature, ceiling height, and surface textures are all precisely calculated to create optimal acoustic conditions for different types of ceremonies. The engineers understand how different geometric shapes affect sound transmission and have developed architectural vocabularies that enhance acoustic performance while maintaining structural integrity and aesthetic appeal. The engineering of the reverberation control systems is equally impressive and scientifically sophisticated. Different religious ceremonies require different acoustic environments. Some need long reverberation times for chanted prayers that create mystical atmospheric effects. Others require clear speech intelligibility for instruction and communication. The engineers have developed architectural techniques that allow acoustic tuning for different purposes within the same space. You notice the incredible sophistication of the sound focusing systems and directional acoustics. Curved walls and ceilings concentrate sound energy at specific locations, allowing priests to speak quietly while ensuring their words reach every worshiper with perfect clarity. These acoustic focusing systems use precise geometric calculations that rival modern acoustic design while creating dramatic effects that enhance religious experience. The engineering of the acoustic isolation systems prevents unwanted sound transmission between different areas of the temple complex. The engineers understand how sound travels through solid materials and structural connections, developing construction techniques that minimize acoustic interference between spaces with different functions, while maintaining structural continuity and architectural harmony. Egyptian engineers have also mastered the art of acoustic enhancement through surface treatments and material selection. Different stone finishes, carved textures, and applied materials create surfaces with specific acoustic properties that can be tailored to particular acoustic requirements. The engineers can control sound absorption and reflection by modifying surface characteristics while maintaining durability and aesthetic appeal. The engineering of the acoustic measurement and testing systems allows engineers to evaluate and optimize acoustic performance during construction. They've developed empirical methods for measuring acoustic properties and adjusting architectural elements to achieve desired sound characteristics, using techniques that remain valid in modern acoustic engineering practice. The integration of acoustic design with architectural aesthetics represents sophisticated engineering coordination that balances multiple requirements. Acoustic requirements must be balanced with structural needs, decorative programs, and symbolic requirements while maintaining architectural excellence. The engineers have developed design approaches that optimize acoustic performance while maintaining architectural integrity and religious significance. The engineering of the acoustic systems also includes environmental considerations and seasonal variations. Temperature, humidity, and atmospheric pressure affect sound transmission,
and the engineers have developed design approaches that maintain acoustic performance despite environmental variations, while accounting for seasonal changes in atmospheric conditions. Egyptian engineers have also developed understanding of how acoustic environments affect human psychology and religious experience. They understand how sound characteristics influence emotional responses and have designed acoustic environments that enhance spiritual experiences while supporting the practical requirements of religious ceremonies. And these acoustic engineering capabilities are being applied to increasingly sophisticated projects, creating acoustic environments that serve complex ceremonial and functional requirements while demonstrating mastery of sound science that remains impressive by modern standards.
You're standing atop the Lighthouse of Alexandria, around 280 BCE, the tallest structure in the ancient world, as Egyptian engineers put the finishing touches on their greatest achievement. The Mediterranean stretches endlessly before you, while below the bustling harbor showcases 3 millennia of engineering evolution. This lighthouse isn't just a navigation aid, it's the culmination of Egyptian engineering mastery, a monument that demonstrates every skill these master builders have developed over 3,000 years of continuous innovation and refinement. The engineering achievement represented by this lighthouse is staggering and unprecedented in human history. Rising over 400 feet above the harbor, it requires sophisticated understanding of structural engineering, materials science, and construction logistics that pushes every aspect of ancient technology to its absolute limits. The engineers have solved problems of foundation design on unstable coastal soils, structural stability under extreme wind loads, and construction at unprecedented heights using only human power and mechanical advantage. Watch as the engineers demonstrate their mastery of integrated systems design and technological synthesis. The lighthouse combines advanced optics, fuel systems, structural engineering, and architectural design into a single coordinated whole that functions as both practical infrastructure and symbolic monument. The mirror systems that focus and project light across vast distances represent the pinnacle of ancient optical engineering, while the fuel delivery systems that maintain continuous operation demonstrate sophisticated mechanical engineering and logistics management. The engineering of the lighthouse's foundation represents the culmination of 3,000 years of geotechnical innovation and soil mechanics knowledge. Built on an artificial island connected to the mainland by a causeway, the structure requires foundation systems capable of withstanding earthquake forces, storm waves, and the gradual settling of coastal soils, while supporting enormous vertical loads and lateral forces from wind and waves. You notice how the lighthouse incorporates engineering innovations developed across the entire span of Egyptian civilization and technological evolution. Stone cutting techniques perfected in pyramid construction, hydraulic engineering developed for irrigation systems, metallurgical skills refined over centuries of experimentation, and architectural principles evolved through temple construction, all come together in this single magnificent structure that represents the synthesis of Egyptian engineering knowledge. The engineering of the lighthouse's operational systems demonstrates sophisticated understanding of human factors and system reliability over extended periods. The structure must operate continuously for centuries, requiring fuel systems, maintenance access, and operational procedures that ensure reliable performance Despite the challenges of coastal exposure and continuous operation, while maintaining the precision needed for effective navigation assistance. Egyptian engineers have also created comprehensive documentation systems that preserve their engineering knowledge for future generations and ensure continuity of expertise. Detailed drawings, construction specifications, and operational manuals ensure that the engineering achievements of Egyptian civilization will survive even if the structures themselves are lost, creating a technical legacy that will influence engineering development for centuries. The engineering education and training systems represent equally important achievements in knowledge transfer and professional development. Master engineers have developed sophisticated apprenticeship programs, technical schools, and knowledge transfer systems that ensure engineering skills are preserved and continuously improved across generations while maintaining quality standards and advancing technical capabilities. The integration of engineering with other disciplines, mathematics, astronomy, medicine, and natural philosophy, demonstrates the sophisticated intellectual framework that supports Egyptian engineering achievement. The engineers haven't just developed practical skills, they've created comprehensive understanding of the natural world and humanity's place within it, establishing the theoretical foundations that support practical engineering applications. The engineering impact extends far beyond Egypt itself and influences technological development across the known world. Egyptian engineers have trained foreign students, consulted on projects throughout the Mediterranean world, and established engineering principles that will influence construction for centuries. Their achievements represent humanity's first systematic approach to large-scale engineering that serves as a model for all subsequent technological development. Egyptian engineers have also developed sophisticated understanding of engineering economics and resource management that optimizes project outcomes. They can calculate project costs, optimize resource utilization, and coordinate complex supply chains that support massive construction projects spanning decades while maintaining quality standards and meeting budget constraints. The quality control and standardization systems ensure that engineering achievements maintain consistent excellence across time and geographic regions while advancing technical capabilities. Standard measurements, material specifications, and construction techniques create engineering systems that function reliably regardless of local conditions or individual variations, while supporting continuous improvement and innovation. And as you look out from this lighthouse across the harbor, where ships from throughout the known world seek the guidance of Egyptian engineering achievement, you realize that these engineers have truly become the master builders of their age, creating works that will inspire and challenge engineers for thousands of years to come, while establishing the foundations of engineering science. As our journey through 3 millennia of Egyptian engineering mastery draws to a close, you find yourself back in the present, but forever changed by witnessing the incredible achievements of these ancient master builders. The engineers of Egypt didn't just construct monuments, they created a civilization that would inspire and challenge humanity for thousands of years, establishing the foundations of engineering science and demonstrating the power of human ingenuity applied systematically over long periods. From those first mud brick makers working beside the flooding Nile to the master engineers who carved temples from living rock, we've witnessed an evolution of technical skill and engineering vision that represents one of humanity's greatest achievements. These weren't primitive builders struggling with crude tools. They were sophisticated engineers who developed mathematical principles, construction techniques, and technological innovations that remained unsurpassed for centuries, while serving as the foundation for all subsequent engineering development. The Egyptian engineers mastered every aspect of their craft through systematic development and continuous innovation. They became precision mathematicians who could calculate astronomical alignments spanning millennia, understanding celestial mechanics with accuracy that rivals modern astronomy. They developed hydraulic engineering systems that controlled the mighty Nile and transformed desert into fertile farmland, creating water management infrastructure that served as models for hydraulic engineering. They created metallurgical techniques that produced tools and weapons of unprecedented quality, developing alloys and heat treatments that provided technological advantages. They pioneered architectural innovations that created the most magnificent buildings in the ancient world, pushing structural engineering to limits that wouldn't be exceeded for over 1,000 years. But perhaps most remarkably, they developed systematic approaches to engineering education and knowledge transfer that ensured their achievements would be preserved and continuously improved across generations. The apprenticeship systems, technical documentation, and institutional structures they created became the foundation for all subsequent engineering development, establishing professional standards and educational methods that remain valid today. Their influence extended far beyond Egypt itself, shaping technological development across the ancient world. Egyptian engineers trained students from throughout the Mediterranean, consulted on projects across known civilization, and established engineering principles that guided construction for centuries. The techniques they developed spread throughout the ancient world, influencing Greek architecture, Roman engineering, and construction practices across all subsequent civilizations. The engineering achievements we've explored represent more than just technical mastery. They demonstrate humanity's endless capacity for innovation, problem solving, and the pursuit of excellence under challenging conditions. The Egyptian engineers faced challenges that would daunt modern engineers, moving stones weighing hundreds of tons without powered machinery, creating structures that would remain stable for millennia, coordinating projects spanning decades with thousands of workers, and achieving precision that rivals modern capabilities using only hand tools and human skill. Their solutions required not just technical knowledge, but creativity, persistence, and vision that pushed the boundaries of possibility. They had to invent new techniques, develop new tools, and create new organizational systems to achieve their ambitious goals. They had to balance practical engineering requirements with artistic vision, religious significance, and political demands while working within the constraints of available materials and human capabilities. The legacy of Egyptian engineering extends far into the future and continues to influence modern practice. Modern engineers still study their techniques, analyze their structures, and learn from their innovations while applying their principles to contemporary challenges. The principles they established, precision measurement, systematic planning, quality control, and integrated systems design, remain fundamental to engineering practice today. Their achievements demonstrate that human ingenuity and determination can overcome seemingly impossible challenges when applied systematically over long periods. As you reflect on this incredible journey through Egyptian engineering history,
Consider how these ancient achievements continue to inspire and challenge us today while providing models for excellence. The Great Pyramid remains one of the most precisely constructed buildings in the world, demonstrating construction accuracy that modern machinery struggles to match. The irrigation systems they developed still influence modern hydraulic engineering and water management practices. The construction techniques they pioneered continue to be studied and applied in contemporary projects, while serving as inspiration for new innovations. But perhaps the most important lesson from Egyptian engineering mastery is the understanding that great achievements require long-term vision, systematic development, and commitment to excellence across generations. The Egyptian engineers didn't achieve their mastery overnight. They built upon the work of their predecessors, continuously refined their techniques, and passed their knowledge to future generations who would achieve even greater things, creating a legacy of continuous improvement and innovation. Their story reminds us that engineering is fundamentally about solving problems and improving human life through systematic application of technical knowledge. Whether building monuments to honor the gods, creating irrigation systems to feed the people, or developing construction techniques that would enable future achievements, the Egyptian engineer demonstrated that excellence requires not just individual brilliance, but systematic approaches to education, quality control, and continuous improvement that ensure knowledge is preserved and enhanced across generations. Their institutional structures, educational methods, and professional standards created a foundation for engineering excellence that enabled achievements spanning millennia. As you drift off to sleep, carry with you the inspiration of these master builders who transformed the impossible into reality through skill, determination, and engineering excellence applied systematically over 3,000 years. Their achievements remind us that with proper knowledge, systematic approach, and unwavering commitment to quality, human beings can create works that will inspire and endure for thousands of years while serving as foundations for even greater achievements. The Egyptian engineers truly became master builders over their 3,000-year journey, developing from simple mud brick makers into sophisticated technical experts whose achievements remain among humanity's greatest accomplishments. Their legacy continues to guide and inspire engineers today, proving that the pursuit of engineering excellence is truly timeless, and that human potential, when properly directed and systematically developed, knows no bounds. Sweet dreams, and may you find inspiration in the incredible achievements of these ancient masters who learned to build for eternity while establishing the foundations of engineering science that continue to serve